The most critical device on the electrical network is the circuit breaker, as it switches off the electrical energy during both normal and fault conditions. Circuit breakers, used in air-insulated substations, come in all shapes and sizes, and in part 1 of this two-part section, we will introduce the principles behind dead tank circuit breakers. By the end of this section, you will understand all of the basic features of dead tank circuit breakers, and see how the circuit breaker contacts break the electrical arc under both normal and fault conditions. The aims of the course today are: introduce the different types of outdoor circuit breakers that we use in air-insulated substations. Look in detail at dead tank circuit breakers. Look at what happens to the arc when the circuit breaker contacts open. Circuit breakers have the following symbol. Firstly, for a single-phase circuit breaker, we use this symbol or this symbol. This is the circuit breaker in the open position. In the closed position, we use this symbol. Next, for a three-phase circuit breaker, we use this symbol or this symbol. All circuit breakers have a rating plate. Here's a typical example. Obviously, the information shown on the rating plate will vary from circuit breaker to circuit breaker, but you will always see the following key parameters. Firstly, we have the rated voltage. This is the maximum system voltage that the circuit breaker can carry. The main impact of the system voltage on the circuit breaker design is how we decide to break the arc as the circuit breaker contacts separate. Next, we have the basic insulation voltage level, or BIL. The circuit breaker is not designed to make or break the basic insulation level voltage, but it does need to be able to withstand it, and the circuit breaker is tested at this voltage level in both the open and closed position. Next, we have the rated continuous current. This is the maximum system current the circuit breaker can carry continuously without being overloaded. The main impact of the current on the circuit breaker design is the physical size of the conductors. The higher the current, the bigger the cross-sectional area of the conductors will be. If the current level exceeds this rated value, the conductors will start overheating, and eventually the temperature will run away, as the circuit breaker will be unable to dissipate the excess temperature. Finally, we have the short circuit current level. This is defined by the system requirements. The circuit breaker needs to be able to withstand the full short circuit current level for 1 second, and is also designed to make and break this level of fault current. We use two main families of outdoor circuit breakers: dead tank circuit breakers that look like this, and live tank circuit breakers that look like this. Let's look at these two families in more detail. The decision on whether to use dead tank or live tank circuit breakers depends on the substation configuration required and the space available for the substation. Nowadays, dead tank circuit breakers tend to be used on circuit breakers up to 66 kV. Above this level, the cost advantages of live tank circuit breakers comes into play, even when we take into account the cost of the additional current transformers. Above 132 kV, single-phase circuit breakers tend to be required, and therefore we have to choose live tank circuit breaker designs. Let's look at dead tank circuit breakers first. Here are some typical dead tank circuit breakers. Let's look inside the circuit breaker to see what's going on. Firstly, we have two bushings, bringing the power into the circuit breaker and taking it out again. The circuit breaker bushings will have the same creepage distance as the other insulators inside the substation, as they suffer from the same pollution and environmental constraints. We have the dead tank itself. Depending on the voltage rating and the circuit breaker design, this may contain an insulating medium such as oil or SF6. We have the mechanism box for the circuit breaker, which contains all of the push buttons and control equipment that operate the circuit breaker. One useful feature of dead tank circuit breakers is that we can put current transformers on both the in and out bushings, therefore monitoring both sides of the circuit breaker. This will reduce the overall physical size of the substation bay, as separate current transformers are no longer required. Next we have the fixed contact and the moving contact. These are what fulfill the main purpose of the circuit breaker, which is to disconnect the electrical supply both during normal and fault conditions. At the moment, the circuit breaker is shown in the closed position. The current flows down one bushing, through the circuit breaker contacts, and back out through the other bushing. Let's now open the circuit breaker. The mechanism box now operates linkages that move the contact downwards, disconnecting the electrical supply. The insulating medium then flows into the gap between the contacts, quenching any electrical arc that may form. Let's now see what happens as the circuit breaker contacts open. Here's a representation of the contacts, with a graph showing the voltages and currents over time. The contacts will open in a very short time scale, either 10 or 20 milliseconds. Let's now slow this sequence down to see what's happening. Here we have two waveforms showing the system voltage and the current passing through the contacts. As the contacts open, the current and voltage will continue to flow, and an arc will be formed, bridging the gap between the contacts. The current will then pass through zero. If the distance between the contacts has reached a certain magnitude, and the arc can no longer bridge the gap, the current will stop flowing, whilst the voltage on the system continues. To see what's happening in more detail, we need to measure the voltage across the contacts. Let's now superimpose that on our system voltages and currents. Let's now close the circuit breaker again and see what happens. Let's now pause this for a moment to see what's going on. At this point, the system voltage is normal as expected. Current is flowing as an arc has formed between the contacts, maintaining the circuit. What about the voltage across the contacts? Well, the arc that's formed between the two contacts means that they are still electrically connected together. The gap between the contacts has a resistance, and where we have current and resistance, we will get a small voltage difference. Let's carry on. Let's now pause it again. As the current waveform passes through zero, the arc now stops. Because the two contacts are no longer electrically connected by the arc, the full system voltage now appears across them. Let's carry on. What's going on here? The arc is attempting to re-establish itself and break down the medium in between the contacts. That's why the voltage across the contacts keeps oscillating. This voltage oscillation, when the current crosses zero, is called the restriking voltage. If the rate of rise of restriking voltage is less than the rate of rise of dielectric strength of the medium between the contacts, then the arc extinguishes and the circuit breaker successfully switches off the electrical supply. Let's now close the circuit breaker and see what happens if the arc successfully bridges the gap between the contacts. This time, the arc reforms and manages to bridge the gap between the separating contacts. The contacts now continue to open, and hopefully, by the time we get to the next current zero, there's sufficient distance between them to switch off the current. Why did it work this time? Well, because there's more insulated medium in between the contacts now, the gap in between the contacts has a higher dielectric strength, which the restriking voltage cannot break down. Therefore, If the rate of rise of restriking voltage is greater than the rate of rise of the dielectric strength of the medium in between the contacts, then the arc continues until the next current zero. If this situation continued when the breaker was fully open, and the dielectric strength between the contacts was still insufficient to clear the arc, the circuit breaker would fail, and the contacts would start melting. So therefore, it's important to design a circuit breaker that can clear the arc within 1 or 2 current zeros. To do this, we need to choose the right insulated medium to insert between the separating contacts. What are the key circuit breaker design features to take away from this section? Well, firstly, as we pull the contacts far apart, we increase the dielectric strength of the gap in between the contacts, which reduces the chance of the arc reforming. So as a designer, our aim is to pull the contacts apart as quickly as possible. Secondly, the dielectric strength of the material in between the contacts is key to the arc reforming. So if we use a high dielectric strength material in between the contacts, we can stop the arc reforming. We will look at how we achieve both of these aims in the next section. The restriking voltage has a very important role in the arc extinction process. If the restriking voltage rises more rapidly than the dielectric strength of the medium between the contacts of the circuit breaker, the current will carry on flowing. One way that we overcome this issue is by increasing the distance between the contacts, which will increase the dielectric strength of the gap. This is done as quickly as possible to limit the damage done by the arc, and most high voltage circuit breakers have an operating time of less than 30 milliseconds. For higher system voltages and currents, pulling the contacts apart in air is not sufficient to overcome the restriking voltage. For these situations, we need to insert a medium in between the separating contacts to increase the dielectric strength. Let's summarize what we've learned today. Dead tank circuit breakers are used widely in air-insulated substations. They have the useful feature of being able to house current transformers in their bushings. The dielectric strength of the material in between the separating circuit breaker contacts is key to whether the circuit breaker stops the electricity flowing or not. It is important for the circuit breaker to clear the fault quickly so that the system can be restored and we avoid damaging the circuit breaker contacts. Congratulations for completing this section. You should now be able to identify all of the key elements of a dead tank circuit breaker and appreciate how important the current zeros of restriking voltages are when the circuit breaker contacts are trying to disrupt the electrical arc. I've attached some questions on today's section to test your knowledge.